Okay, so today it's a little bit of a step up in complexity from the previous sort of single qubit or XOR problems, but to a more standardized, perhaps in the quantum realm, algorithm. Specifically, this video is on the quantum approximation or approximate optimization algorithm, or QAOA, as you will often see it in literature. And this is perhaps the second most famous quantum variational algorithm, only behind the variational eigensolver, which I'll actually be doing a video on that later. But before I actually introduce what the quantum approximate optimization algorithm actually looks like, I'm going to talk about the problem setting used in the original paper. I'll link that and a bunch of relevant papers in the description. Using the original paper and just the standard by which it is evaluated frequently, which is the max cut problem. So for those of you who have, if you remember back to your algorithms class, you probably learned about this. It's a very difficult problem, and by difficult I mean NP. I think it's NP complete, not 100% sure, but this algorithm is specifically a graph algorithm in which your goal is to find the two sets of vertices that you can cut the maximum number of edges between. So for example, if you have a simple graph that looks like this, max cut would be 4, because you can make two groups of vertices if you imagine, there's a scissors cutting through here, 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 and here. So you can see you cut 4 edges. So the max cut in this case is 4. And this gets, you can imagine, very complex very quickly if you have thousands of nodes and even more and more edges, a densely connected graph where one node is connected to every other node. There's an insane amount of computation there. And so there's a lot of approximate, both classical and quantum algorithms for this. And so this is just the setup of the problem that we're evaluating right now. And so first, now that we have the simple problem, let's just consider what it means to solve this problem. We want something that maximizes. It's a maximization problem. We want to max this cost function, which is basically just the number of edges cut. And so, yeah, it is an NP complete problem, by the way. And so we can say this is a function of the and so there's some constraints on this optimization, but that's pretty much the maximization problem. And so now that's just an outline of what exactly the problem setting is. Now we'll get to the solution. So with the solution to this, we basically encode the graph into the quantum circuit, and then we try to optimize the circuit parameters such that we can get the two, it'll tell us the two collections of vertices, and from there we can find the max cut. And so what this actually looks like is if you have labeled vertices, perhaps this could be 0, 1, 2, 3, and this circuit, in this case, the two partitions would look like 1, 0, 0, 1, 0, 1, 1, 0. So what these states represent is there's the same number of qubits as there are nodes, so there's a scaling laws right there, but this is saying okay, in this partition, we have node 0 and node 3. Don't read this as the binary. This is, let's see, 1, 2, 4. This is, 8, it's 9 in binary. We don't want to read that as binary. We want to read this as, this is, node 1, node 2, node 3, or 0, etc. And that's really what we want to see this as. And so in order to solve this problem, I'll just put this at the beginning perhaps. We construct the circuit with a certain number of layers. And we've seen layers in a lot of different, you'll see them in a lot of different variational algorithms. You'll see them in deep learning. But basically, we construct a circuit of, let's make a new page for this, of p layers. I don't remember why they used a variable p in the original paper, so you can get on them about that. So we have p layers, and so now this is where we have our circuit that we're applying to the initial state. And so we can say that the variables are typically beta is what they're abbreviated, beta and gamma. Should do beta j and gamma j. And this is all applied on the initial state, which is initial. Usually this is you just apply Hadamard gates to every single qubit to get a equal superposition. And so this is what the circuit basically looks like. So what's going on here? Let's talk about first, how do we get this concept of a graph into a quantum circuit? Or what's the representation for this quantum circuit? And so there's a lot of background here. You can look into adiabatic quantum computation and Ising models and stuff, but there's lots of interesting topics with combinatorial optimization problems in Ising models. But in this case, just let's specifically look at how do we get this state into, or this graph into the quantum circuit. And so the answer is pretty straightforward, actually, if we remember that. And so the way this is done is via the cost Hamiltonian. And so if we remember the original maximization problem, we can consider that the max cut, if we're maximizing C of z, this cost, this is the same thing as maximizing, that's really bad, the sum over the edges of this separate function. We do this, where we can consider this to be is equal to the 1/2 1 minus. So these are the z, I should specify z, the z Pauli operators for the two nodes that it connects. So if we have the example of the 4-node graph above, this is maximized when these two measurements are different. And so if these two nodes basically are not in the same section, and so for example, we can see why, if we had 0, 0, 0, 0 and 1, 1, 1, 1, this would clearly not maximize this. So this is not the answer that we're looking for. This is clearly minimizing it because it, this isn't even really an answer. There's, this is the empty set partition, I guess. And so this barely even counts as an answer, but it definitely doesn't maximize it. And so this is you'll see this cost Hamiltonian. So this is really what we're trying to get, via the answer, and how we're trying to get the answer. And so what we can do is we can encode this into a quantum circuit using this exponent. If we write this in an exponential form, which I'm probably familiar with, in quantum computing is really common using exponentials, we can write it parametrized via this, and these are the two nodes. I shouldn't use I actually here because we already have an I that represents the imaginary number. And so those are the cost, that's the cost Hamiltonian. And so this is, you can encode this into a quantum circuit. Specifically, this becomes a, if you're looking to hard code this, a lot of programs like we'll see have an exponential function, but this becomes the C0 followed by these are 2 qubits, followed by another C0, and this is RZ parametrized by gamma. And so this is essentially the cost Hamiltonian. And so we can see how we would encode this into a quantum circuit because we have, we know the graph, so we know the details of the graph. So for every edge, we simply take the 2 nodes and we apply this gate, this 2 qubit gate to each of them. And so really this is really over every J and K. This is just a specific instance I should specify. And so then we can see we have a parameter. Ultimately, we have a single parameter that details this cost Hamiltonian. And we can see now that we can encode this into a quantum circuit. And so from here, we can, after you go through every edge and you apply this 2 qubit operations to the 2 nodes of every edge, you've basically set up the operation. You've set up the cost Hamiltonian. And so now what you want to do, you might be thinking, okay, let's just optimize this straight out of the box. But it's important to consider that just optimizing it right out of the box won't actually get you very good results because you're just applying, this is you're just going to end up when you apply this operation on the initial quantum state, you're just going to end up with some a limited number of solutions because you're only going to end up in when you apply an operator on a state, you only get the results are eigenvalues of that operator. And so we're constrained there. And that's why you'll also see the mixing Hamiltonian. And this one's a lot easier to do. It's usually just, so we want something that, specifically in this case, we're looking for a non-commuting operator. So specifically we know that the Pauli matrices do not commute. Then we can say we can have different results if we, for example, construct a mixing Hamiltonian of the form e to the negative I beta, where this is just the Pauli X gate that I've written here, and this typically it gets converted to a circuit via Rx to beta, but you'll see something different in TensorFlow Quantum just due to how they implement their exponential function. And so you can see we can rewrite the final sort of circuit as this function of which is equal to these Hamiltonians, where we do j equals 1. So we apply first the cost Hamiltonian, and so it's important to recognize that this is opposite the intuition. The second the second exponential is actually applied first. So then we can do the mixing Hamiltonian. Then this is b j gamma j, the cost Hamiltonian, and so that is just applying this unitary parametrized by a specific beta and gamma p times with 2p parameters. So we can see that this usually has not as many parameters to optimize as other works. With like the QDQN paper, there was 50 parameters maybe to optimize this. You can't have many layers to this. You usually see for really good analysis 8 to 12 layers, which is only 16 to 24 parameters, which is a lot easier to optimize. At least from a computational expense standpoint, the techniques of optimization might be different. And so this isn't really meant to be a complete review of the actual algorithm. There's tons of resources out there that exist. This is just setting the stage for how to do it in TensorFlow Quantum. So, if you came in here expecting from the ground up QAOA, this is not it. Just background so we can see how to do this in TensorFlow Quantum. And so this is pretty similar in the TensorFlow white paper. They do have an example of QAOA. This is different, slightly different from that, and it also allows for multiple layers. And so let us now get into that. We can see I have two different files that we're going to see. Let me hide this, show this. And so first, got to zoom in here. We can see this is the first one, which is the only difference between the two is their optimization. This uses a non-gradient based optimization, specifically Nelder-Mead, I think is what that one uses, but you can change it to be a lot of different things because I just used the SciPy optimize minimize function. And so first, let's just do exactly the graph. Let's go over to code first, and then I'll show what this optimization procedure looks like. So this is just typical import. Specifically for the graphs, we use network X, which is pretty standard. I set a random seed specifically here because I found that this optimization is this might just be my implementation, but the optimization can be kind of hit or miss. And so, yeah, that's just why I specify random seed and a specific larger graph is because I know this one will work. And so sometimes they don't work. I don't know. There's lots of details on how to optimize them and learn these functions. And so that's not something I'm going to get into, but it's not a perfect algorithm. And so here we can see we're just making the graph, random regular graph. In this case, I'm going to make that square graph that I drew earlier. And so first we create the qubits. So we have our one qubit for every node as detailed. And so first we have this initial superposition. So we just apply the Hadamard gate on every qubit, and then we construct our mixing Hamiltonian. And so we can see that for every qubit, we want to apply the X gate. Keep in mind, we're relying on the built-in exponential function. And so here we have the cost Hamiltonian, and we can see that we have this constant at the beginning, just this 1/2, and then we add the 1/2 times the z on the first qubit and a z on the second qubit, because this, remember, this is for every single edge that we do this. And so that's exactly what this formula, that's exactly, if I go back, that's exactly what we're doing here. This is just applying that z operator on all of them, on every qubit on an edge. So now we have, you can see it's really easy to do in TFQ, and which is good. Each Hamiltonian takes only 3 lines of code, very simple. So now we want our final circuit. We can specify a depth here, and I just use A and B for their parameter names. And so then we can see we do the exponential, and so we want the cost Hamiltonian first, then the mixing Hamiltonian, and then we have the parameters. And so we do that for, however many times we need the depth. And then we convert the initial to tensor. I can get rid of this. And we see that it's pretty standard from here in. The input is just the same for every single optimization loop. It's just the initial superposition. We declare a data type of string for the input, which is always standard because the TensorFlow quantum serialized circuits as strings. The output is just the results of this parametrized quantum layer. And so what's happening here is we have this circuit that we're optimizing. And this is one of the great things about TensorFlow Quantum, that if you see in like Penny Lane and stuff, you'll have to write out fancy stuff for the readout operator. But remember, this is the cost Hamiltonian. What this is saying is read it out. This is the readout operator, is the cost Hamiltonian. And so this is exactly, we can see we don't have to do any fancy readout operators, because this is exactly the cost, that this is the measurement that we want, the number that we want to specifically, in this case, minimize in this readout operator. I know I posited the formulation as a maximization problem. However, it's easier to write minimization problems in a lot of optimization techniques, just because that's just the way I have it written. And so we can see that's why up here it's just there's no negative functionality. And so and specifically in this case, we are this isn't necessarily the max cut. This isn't saying, when we measure this isn't, we're not trying to minimize the number of cuts made. That's not what we're doing. It's just the technique used. If we read out in the same cost Hamiltonian basis, then we can minimize that, which will result in a maximization of the cost function. And so it's weird, we say cost and cost Hamiltonian, but keep in mind this is not trying to minimize max cut, and this is not the output, which you'll see as a loss, is not the number of cuts. And so just wanted to clarify that. So in this case, we set up the model as standard. We compile it with mean, absolute error, and typical atom optimizer, and we set it to 0. Here we can see this is just the optimal sort of, you can't get any lower than 0. We fit it for 800 epochs. One thing to note that I'll just comment on, and part of why it's interesting to optimize, is if you do more than 800 epochs, specifically when p is equal to 2, you'll get worse results. And so there's something to be said there about the optimization. Just plot out the loss function, show the variables, and now we want to sample it to actually get the, this will give us, we can see the partitions here easily, but then we want to actually construct and reconstruct what the max cut is. And so we can sample it by creating this circuit here, and then we sample the circuit with the parameters 1,000 times. From there, we can get the predictions, and here we just, you can see this is exactly what I was describing earlier, where we append the position to these predictions. So for example, these are the partitions, specifically the nodes. And so if the quantum prediction is, 0, 0, 1, 1, this will append 2, 3. And so the prediction will be the partition 2, 3. And so this is converting that binary output into the partitions. And so this is what we can do, just because it's this is pretty much exactly from the QAOA TFQ tutorial from the white paper. We can, because it's small enough graphs, we can just create every single combination, and then we can just get the optimal cut size from there. And so in this case, because we're doing small graph, we'll create a histogram, and you can see the partitions. And so here we can get the average cut size predicted by the quantum algorithm, and here we can see the actual optimal output. And so this number is usually lower bounded to be about 0.65, if I remember correctly, for a lot of single layer versions. And there's work that has shown the quantum algorithm with deep layers or many layers can achieve 0.99, 0.98, which is better than classical algorithms. So now I will show exactly what this looks like. Oops, wrong one. Here. And so now we can see exactly what will be going on here. So let me just clear the screen, and then we'll run this, and so it'll open all the libraries, and we can see this is the graph. Doesn't represent it as a perfect square, but you can see these are the 4 nodes. And so now we can just keep that in mind. I'll X out. And so now it'll train, this is depth 1, remember, for 800 epochs. And specifically, this is optimizing with gradients here. And we can see that this is what the loss function looks like. Sort of plateaus down here. And then, so here are the variables. So it says the cost. This is actually sort of reversed of what it would normally be, but we can see this is the predicted quantum max cut, and this is the actual, we said it's 4. And so this is basically the grade of how much it got correct. It's 0.75. And so this is a histogram of what that looks like. So we can see it predicts the partitions 0, 1, 0, 1, and 1, 0, 1, 0. These are the 2 highest. And so if we increase this to depth 2, which I can just X out of I just realized I was not sharing that. So let me just capture this window real quick. Here's the histogram that I accidentally didn't show, but you can see that 0, 1, 0, 1 is max, 1, 0, 1, 0 also max, and so those are the 2 predicted partitions. Now if I X out of that, we can remove capture 4, and then we can change this to be, all I'm changing here is setting p equal to 2 now. And then we run it again. And it's a pretty quick optimization loop. Remember, there's only, in this case, 4 optimization variables. And it's going to print out the graph, which I also realized last time that you were not able to see, but it's the exact same square graph that I drew in the beginning. And so it'll optimize this just real quick. And this is specifically where if you let this train longer, and I encourage you download the code and try training it longer, the loss will shrink. But if you actually look at the sampled average, it will get worse. even though the loss decreases. So maybe a better loss function would be the actual, you wouldn't even need to read out in the cost Hamiltonian direction. You could read out in the z basis, sample the outputs, convert that over, and get an approximate, max cut result. That would be super computationally expensive, but the interesting idea. And so here we can see the parameters, and then it has to sample 1,000 times, so it's kind of expensive. And here we can see a more clearly defined histogram, which I will show this time. If I just go here, yes, you can see that the two partitions are 1 and 2, or sorry, 0 and 1 and 2 and 3, very defined. And this has a lot better. It went from 0.75 to 0.86, so that's a big improvement right there. And so that's basically the extent of how you do it in TensorFlow. Just for one last example, I will go over, I will be running the optimization on this defined graph while I discuss the other optimization strategy. So this one is set up the exact same, except here we use this, we don't compile it via that. We use this optimization function from SciPy, and we can set this optimization to use different methods. In this case, it's one that does not require gradients, and then we just have to define a function of the weights that returns the loss. And so this is pretty easy to do here. And so I'm not going to run this code. It doesn't always yield better results, but it is a common optimization technique that you'll see. And so instead, I will share the larger graph results, which you can see. This is what the actual larger graph looks like. It's 10 nodes, regularity of 3. And so now that we want to optimize that, we can close out and see. This takes a little bit longer to optimize, but not a huge amount, just because with more edges, remember that there's more gates being applied and there's more nodes in the graph, and so there's more qubits. But all in all, still doesn't take that long. And this is specifically with P, in this case, is equal to 2. So just keep that in mind as it minimizes this cost. And so now it reaches the end, and we can see the loss graph. I don't show the loss graphs because they're not that meaningful, but we can see the parameters printed out here. And then we will be able to see the histogram. You might want to comment it out if you're running with the 10, because it's 2 to the 10th, or 1024 possible partitions, which is a lot. And so the histogram doesn't really look like anything. And so this is the final result, 0.65, not that great. So here we can see something interesting. If I reduce P to 1 and redo this process, I expect to get better results, assuming nothing has changed since I last ran this. And so you can see the tricks and the interesting properties of this optimization. So yeah, this will optimize slightly faster because there's half as many parameters. And then we can see that the end result will, I expect, be slightly better, which is interesting because you might expect the result of more depth to be better, which it usually is, but not always. So we're just waiting for the sampling, and yeah, we can see 0.82 is a lot better than the 0.6 that we were prescribed. Of course, you could optimize it more and do different techniques, but that's basically just an overview of how to do the QAOA problem in TensorFlow Quantum. And so code is available, and I encourage people to check it out, play with it, try different things. There might be a room for optimization or little bugs. I found an example of what I assume to be a bug is that if you can make strings alphanumerically, but if you put numbers in the strings of the names of the variables, it actually makes them do worse at optimizing. Specifically, it starts with a higher cost function. So not really sure about that one, but there might be little rooms for optimizations with higher P layers, and so you can check it out. And yeah, that's pretty much it. So that's a quantum approximate optimization algorithm in TensorFlow Quantum.